All right. So today we're looking at the DiVincenzo criteria. So the DiVincenzo criteria are a set of 5 to 7 sort of abstract ideas for criteria required to have a functioning quantum computer. There's actually 7. If we decide to extend the definition to include sort of quantum communication and quantum networks, but we'll get to that later. The first sort of requirement is this scalable register with a well-characterized qubits. Now, this requirement sort of has two requirements in it, namely the fact that the system is scalable and the fact that the qubits are well characterized. So let's look at those individually. So the fact that the system is scalable means that um, we aren't sort of restricted to n amount of qubits. So hypothetically, if you made a really, really high quality quantum computer, which can compute with only 2 qubits, so I don't know, let's just say they're spins, and but you can't scale it. So like this has like a 99.99999% sophistication, but you can't scale it. You can't like add more qubits to extend the dimensions that you can compute with. Then we can't really use it for anything because we never know what sort of challenges it is that we want to tackle in the future. So it might be arbitrarily large. So it would be a restriction to not be able to scale it. And so like by definition or like by the idea extends to the fact that we can scale it to some arbitrary n, meaning you want to just like be able to keep adding qubits for however however long you need. So you can compute bigger problems. That's actually one of the advantages of using quantum computers. It's the fact that we have these like complexity class reductions in known algorithms, at least for some known algorithms, which can be sped up. And the return on investment you get per added qubit is insane, especially when compared to classical computers, meaning that it really is practically essential that we're able to have as many qubits to be computed as possible, as long as it actually maintains a good quality. Now, along with this, it actually says that the qubits need to be well characterized. In other words, we need to actually know what it is that we're doing. So, hypothetically, if we imagined a sort of, let's just call it a black box, and I tell you that this black box is a computer and it can compute anything, you just need to sort of run signals into it. But I don't tell you how it works. You would obviously be confused because what is it that you actually do? Do you throw rocks at it? Do you like shoot a laser beam? Um, do you run like electricity through it? You wouldn't know. And that's why I'm saying like we need well characterized qubits. So what this means is that we understand how it is that we manipulate the states of the quantum system such that it evolves according to a known Hamiltonian, um, or whatever it is that we actually, need to have the qubits function on. So an example would be an atom with 2 known energy eigenstates. If we call it, let's just say, state 1, if we define the qubits as being the ground state and first excited state, and we understand the difference in energy between them, which sort of corresponds to some known frequency that we can perform on it, then we have a well-characterized system because we have defined a qubit as being the known energy states of an atomic system. And because we know the energy difference, that means that we know how it evolves according to a Hamiltonian in response to the frequency difference between them. But that's just an example. In reality, it could mean anything because there are so many different types of quantum computers. There are practically infinite ways to define like what a logical qubit is for a quantum system, but like this is just an example. Anyways, we need to be able to initialize the qubits. This basically just means that part of the logic of operating on qubits is that if you have to perform an algorithm, you sort of start with an initial idea of what the qubits are, or not just idea, but like you have to know what the qubits are before you can perform any sort of operation on them. Um, so, you know, imagine that we had some sort of algorithm, um, meaning every time you wish to perform this algorithm, you simply just repeat the same sort of series of actions. But this wouldn't really make a difference if it was the case that the initialized qubits every time were just scrambled. So the fact that we have to initialize them is because we sort of have to have our initial register, etc. Because that way, anytime we perform an action, it is universally on the same set of qubits. Otherwise, if you don't even know what they are, then you're just producing gibberish. Um, and it's not like you can just map the instructions from qubits, backwards. So you can't just bit flip whatever known qubits are afterwards to some standard, because we know that quantum gates behave differently depending on the qubit. So, bit flip behaves like normally, but something like Hamiltonians don't. It produces different outcomes, which is why we sort of need to have the initial setup be the same every time before it is that we perform any algorithm. Anyways, we need to have long decoherence times, which also ironically means long coherence times. And the reason for that is pretty simple. Quantum systems, qubits, are probably like some of the most sensitive things that exist in the universe. It takes nothing to destroy their coherence. And so you sort of have to technologically develop the tech to maintain long coherence times. Part of this also actually means that we have to have well-developed, sophisticated um, error corrective sort of algorithms and procedures for just making sure that the coherences last long. But yeah, this is essential because uh, maintaining these coherences are in principle the real sort of requirement for this to be an actual quantum computer. Otherwise, if they just decohered, I mean, in a way, you would actually just have a normal classical computer with only just 2 bits, 0 and 1, um, which is why this is important. Another aspect is that the reason we have to maintain a long decoherence is because any algorithm takes some finite time. Evolving qubits according to Hamiltonian, it isn't actually something you can force to happen quicker. It has to happen at some certain rate, meaning some actions you can't actually make shorter than necessary. So if you have a really long, really sophisticated algorithm, you need to have some minimal um, coherence time for that to actually function. And that's without considering the fact that, any operation we do back to back, we try to sort of make the windows between the operations as small as possible So everything can happen as quickly as possible while still maintaining good operative quality. But like you can't force the actual actions themselves. You can only make shorter the gaps between them. And besides that, the way to improve is obviously just to try to make the coherence times longer. Um, for most systems, this actually just means perfecting the hardware. Like for the solid state spins, for example, there was this problem that the atoms in the solid state material had nuclear spins, and these produced magnetic fields which decohered the spin qubit. But the way that they got around this problem was that they just cleaned up the material for isotopes such that it had an even amount of isotopes, which made the spins cancel in the material, which drastically reduced like the environmental noise and thus extended the coherence time. But again, that's just an example. Um, but yeah, like the longer the coherence time, the better. And besides that, if I recall correctly, I think there are also like other procedures for recovering coherence, like a spin echo, if I recall correctly. But yeah, now a quantum computer has to have a universal set of quantum gates. Now, you guys passed quantum computing or intro to quantum computing, so you already know what this is, but just to repeat, um, for a quantum computer to work, you need to be able to, per qubit, produce any possible qubit that exists, which basically means that, you know, we have to be able to go anywhere on the Bloch sphere, anywhere on the surface, preferably, because that means we're in a pure quantum state. In other words, we haven't decohered. But, and what I mean by go anywhere on the Bloch sphere is in principle just, I can't remember. There was this like mathematical definition from Intro to Quantum Computing where it was, just to some small approximation within some small interval around uh, some point within some arbitrarily small like interval. If we can if we have a set of operations which approximates the Bloch vector to go to this place, that means it is or sort of, it has Bloch universality. And besides that, besides the qubits being able to go anywhere on the Bloch sphere, we also need something to produce entanglement between qubits. Whoops. And typically that's just like a C naught, but it doesn't necessarily have to be C naught. I'm assuming you guys read the same scientific articles as I did for this course. And if you did, the solid state spin article, for example, mentioned that they instead used this controlled Z gate instead. But that's like their two qubit operation for producing entanglement, but it isn't a requirement that it specifically be C naught. It's just that as long as you have like a two qubit gate for entanglement and you have Bloch universality, then you have a universal quantum gate, a set of quantum gates. And lastly, for the just local quantum computer, you need a well-defined readout or like a qubit-defined readout mechanism. So this just means that like, yeah, our quantum computer has performed a calculation, but we need to actually be able to extract the result from it. Now, how you extract the result, it depends entirely on the quantum system that the computer is operating on. Um, for example, if you have some atoms, so like if we just draw these as atoms, and that's like your register, if there's like 5 qubits, if you defined a qubit to mean like the energy levels inside it, then the way you'd sort of read out, I'm doing air quotes, read out what their final qubit state was, is that you interrogate which of the two energy levels it is. In other words, you're asking, are you logical 0 or are you logical 1? And for the atoms, as was the used example up here, it would be subjecting them to an electromagnetic field. In other words, shooting with a laser. So it could be, for example, that you shoot them with a laser, and whether or not they light up or not, so if they have fluorescence, they are either in 0 or 1 or something like that, you know. Uh, but again, it's different for every quantum computer. Um, Now, for the extended criteria, that's if you're trying to do like quantum communications or like build a quantum network. There are two additional sort of requirements. First of all, there's this stationary flying qubit interface. Basically, if you have some computer, a quantum computer, and sure, it can compute quantumly, but you want it to also be able to communicate with another quantum computer that's far away. The way you do it is that you have sort of like your operations be done here, and whatever result you have or algorithm you need to perform or whatever, you want to be able to convert the results of the qubits into quantum information, which gets transmitted to the other computer, and it has to be done while maintaining the quantum nature. So you can't just like read it out and then send classical information. We already do that. I mean, that's how we did things with coding using IBM Q. So assuming your quantum computer isn't already operating with some flying qubits, it needs to convert its logical qubits into logical flying qubits. Now, there's basically only one real way of doing this. The only feasible way is photons. So, in other words, you need to be able to produce photons, which are then, let's just say, shot at the other computer via whatever channels uh, are available. Usually, it's like, what's it called? Optical wire? I forgot, a fiber or something. I forgot what the name was. But yeah, it's because photons are so fast and they're sort of easy to control. We know how to control them. It's just there are a few challenges with improving the purity of optical fiber to maintain coherence. But once you also sort of develop good enough tech and are able to minimize faulty wires, this transmission is sort of the only feasible way of doing real quantum communication between two quantum computers or two quantum systems which are spatially separated. Um, and this also sort of relates to the last requirement, which is faithful qubit transmission. In other words, this just means that our qubit doesn't mess up along the way. We don't have a bit flip, we don't have a Z flip, or even if we do, then we're aware of it and know how to correct for it. So sort of, flying qubit error correction. But yeah, this really just means that, we don't have any operational errors and we don't have any decoherence effects. In other words, if you send some logical qubit, it has to arrive as the same logical qubit. And this is easier said than done because this is actually sort of just about improving the quality and fidelity of the tech itself until it is that we get some sort of like a minimal rate at which this is successful. Uh, Probably at like as soon as like we're at like 99% fidelity rate, then it should be fine, is my guess. But what do I know? I hope it makes sense what I'm saying. Um, but yeah, those are the five DiVincenzo criteria, and thanks for listening.